All right, in this video, we're going to go over standard deviation and z-scores. But before we do that, I want to touch on the concept of skewedness of a data set. So a data set is skewed if a large percentage of the data values are either concentrated to the left or to the right. Okay? So basically what you're going to do to determine skewedness is that you're going to look at histograms, basically. And what I like to do is I like to draw a curve that kind of mimics the height of the bars of the histogram. And I like to observe the tails, okay? If I have a longer left tail, that means I'm left skewed, what we call left skewed. If I have a longer right tail, what we call right skewed. For example, here's some examples of skewed distributions, skewed data sets, okay? So here, this is a skewed left distribution because if I were to draw a curve that kind of follows the height of those bars of that histogram there. Okay, and what I like to do is I like to cut it off at this peak. Okay, so right there, that's our peak. And from that peak, look to the left and look to the right. Notice that the left tail for this is significantly longer. Okay, to the left of that peak, that tail is longer than to the right. Therefore, this is a skewed left distribution. Long left tail, skewed left. Long right tail, you are skewed right. I see this. So if the peak is somewhere up in here, we have a longer right tail. If the left and right tails are approximately the same length, then we have what's called a symmetric distribution. So here we have a symmetric distribution. All right. And so another way that we can tell whether or not a distribution is skewed left or skewed right is the comparison of the mean and the median. Okay, how does the mean, a little neater here, how does the mean compare to the median for a skewed left distribution? Well, if you recall, the median is the middle data value. Okay, so your median tends to be where the data values are clumped the most. And because we're dealing with histograms, that means that wherever the tallest bars lie, basically the peak of that curve that you drew, that's going to be where the median is going to be located. However, a mean, as I said in the previous video, is more affected by smaller values. So if you have a skewed left distribution, what's happening is those small values is pulling that mean to the left of the median, right? If you take an average and you're adding smaller and smaller data values, that average becomes smaller and smaller. So for a skewed left distribution, the mean is less than the median. Look, folks, all you got to realize is that if the mean is less than the median, it's skewed left. And you can memorize that by saying, look at the way the arrow is pointing there. The arrow is pointing to the left. It's a left skewed distribution. The opposite is true for skewed right. For a right skewed distribution, the mean is actually going to be greater than the median. Because once again, the median is going to be where the tallest bars are, the peak of the curve that we drew. But because we have some larger values, that's pulling that mean to the right. And then lastly, for symmetric, the mean should be approximately the same as the median. Okay, so that's how you know you have a symmetric distribution. If your mean is kind of close to your median, you have a symmetric distribution. Okay? So here we go. So a data set, for example, a data set of the score in a class for elementary statistics in a junior college has a mean of 78 and a median of 69. Which of the following is a logical conclusion regarding the shape of the distribution? Meaning, are we left skewed, right skewed, or symmetric? Okay, so we're going to compare the mean to the median. Okay, I like to put the mean on the left side. That's how you match up the directions. Okay, our mean was, let's see, 78. Our median was 69. So 78 is greater than 69. So our mean is greater than the median, which indicates we're going to have a right skew distribution. Okay? A right skew or skew right distribution, doesn't matter. This is the right. Okay. So now we're going to get into a very important concept in statistics, and it's the measurement of spread. What I mean by that is how much are your data values dispersed, or how far apart are your data values from each other. And so way back when we did I did the video on the what was it, on frequency tables, and remember we had classes and we had to find the range. Well, the range is the most basic measure of spread, but it's not really that good of a measure. And so instead what we have is something called population, or what we have called variance. We have both population variance and sample variance. Because remember, there's two different types of data sets. You have population and you have samples. So a population variance, what it is this the average of the square of your deviations. So what the heck is a deviation? A deviation is a measurement of how much a data value is different than the mean. Just like in society, whenever you're a deviant in society, it means that you're different than being normal or average. Okay? So the population variance, and we have this symbol for population variance, we have this symbol called sigma squared. Okay, so let me see here. It's like an O with the backwards hat. I don't know how to explain that. But this is called sigma, we read this as sigma squared. Okay. And so what you have here is a formula, which we'll use in a second, but I'll try to explain it. The formula is, so whenever you see this notation here, this notation means you're adding something up or you're summing. So what you're going to do is you're going to sum, you're going to take your data value minus the mean, and you're going to square that. And you're going to add that up for each of your data values. And then you're going to divide by n. If you remember from the previous video, n is your population size. All right. On the other hand, the sample variance, we get a slightly different formula. So this is our first foray into seeing that in statistics, sometimes you're going to get a different answer based off of whether or not you're working with a population versus a sample. So a sample variance is the formula s squared, and once again, you take your data value, subtract away, and I apologize there, that should not be mu, that should be x bar. So you take your you take your data value, subtract away the sample mean, and you're going to square that up, and then this time you divide it by, not by your sample size, because remember n, lowercase n represents your sample size, you're actually going to divide it by n minus 1. And the reason for that is because it's a correcting factor. Because you don't know all this information, you just can't divide by n. You have to divide by n minus 1. Okay, I promise we're going to get into some examples in a second. It's going to make a lot more sense. So notice that the units for the variance are squared because we are squaring what we call those deviations. All right, therefore, instead we like to use something called the standard deviation. And what the standard deviation is the square root of the variance. So the units for standard deviation are going to be to the first power, units that we are used to. And so to calculate your standard deviation, all you do is you take the square root of the corresponding variance. So for population standard deviation, you take the square root of the population variance. For sample standard deviation, you're going to take the square root of the sample variance. And notice the symbols. Notice variance had that second power, but standard deviation does not have that second power. So that's the indicator of what your units are. All right, so here we go. I refer to this as a circle of life in stats. You need to be comfortable being able to maneuver between variance and standard deviation. So keep in mind, variance has the symbols either a sigma squared or an s squared, whereas standard deviation will be the same symbols, just take away the second power. So what is this diagram going to show you? I want this diagram to show you what happens if you have the variance and you want to calculate the standard deviation. Well, as I just told you, you're going to take the square root of something, okay? You take the square root of your variance. That's what the dot means there. Take the square root of your variance. So if you know your variance, you're trying to get to your standard deviation, you take the square root. But what if you know the standard deviation and you're trying to get back to the variance? In that case, you're going to square the standard deviation. Okay? All right, there we go. some examples here. For example, calculate the standard deviation for the following data values. Assume the data set is a sample. So what we're going to do here is the first thing we have to do is we have to calculate the mean, in this case the sample mean. All right, so the sample mean, x bar sample mean, will be 7 plus 15 plus 8 divided by 3. Okay, so 22 plus 8 is 30 divided by 3. We actually get a nice mean of 10 there. Okay. All right, so now this is what we do. To calculate the sample variance, because our data set is a sample, to calculate the sample variance, S squared, what you're going to do is you take your first data value, in our case it's 7, and you're going to subtract away the mean of 10. You're going to take that difference, 7 minus 10, and we have to square it. Okay? That's where, let me see if I can highlight it. If you go back to the formula, that's what we're doing here. Okay? We're taking the data value, x is the data value, minus the mean, and then we are squaring it. And we're going to add, remember we're summing up all of these squared deviations. We're going to add to that now the next data value. 15 minus the mean of 10, still need to square it. Plus, so you just keep on doing this for all your data values. Plus, lastly, we only have 3, 8 minus 10, quantity squared. And then we divide this by, because it's a sample data set, we're calculating sample variance, we're dividing this by n minus 1. Very important difference, okay? So because it's a sample, we are going to divide that sum, that numerator, by 3, because there's 3 data values, minus 1, which is 2, of course. And so, very important, y'all. So if this had been a population, instead we would divide by 3 instead of the 2. All right, so let's quickly calculate this. 7 minus 10 is a negative 3. We still need to square it, plus, let's see here, 5 squared, plus a negative 2 squared. Just worked out the subtraction there, divided by 2. So we get 9 plus a negative 3 squared is positive 9, 5 squared is 25, plus 4 divided by 2. What's that? 9 plus 25 plus 4 gives us 38 divided by 2, which gives us 19. So the sample, excuse me, that's the sample variance. I don't need to box that up. This is the sample variance. Okay, but the question said find the sample standard deviation. So the sample standard deviation will be the square root of that 19, which gives us approximately, pull up my calculator here, that I do not know. The square root of 19 gives us, to 2 decimal places, let's do 4.36. 4.36. Okay? So in of itself, the standard deviation doesn't really give you a ton of information, but we can use it for comparison's sake. If I have one data set that has a standard deviation of 4.36, and I have another data set that has a standard deviation of, let's say, 10.6, that means that that data set that has the standard deviation of 10.6, those data values are going to be more spread out when compared to the data set that has a standard deviation of 4.36. So that's what your standard deviation measures. All right, here we go. Suppose that the standard deviation of a data set is 4.86. What is the variance of that data set? We're going to round it to 2 decimal places. Okay? So remember, go back to our diagram, the circle of life. All right, if we know the standard deviation and we're trying to get over to the variance, that means that we need to square the standard deviation to get to the variance. So Here we already know the standard deviation. Okay, so the variance is the square of that 4.86, which to 2 decimal places will be 4.86 squared to 2 decimal places is 23.62. All right, there we go. All right. Okay. So once again, standard deviation is a measure of how compact or how spread out your data values are. So here's the application of it. 2 companies, A and B, they sell little packets of saccharin, fake sugar. The mean and standard deviation for the samples from the respective companies is provided below. Which company consistently produces extra saccharin in their packet? Which company fills its packets more consistently? Okay, let's answer the first question. Which company produces extra saccharin in their packet? Okay, which company produces the extra saccharin? I'm not going to spell that whole word. Well, to see who produces the extra saccharin more frequently, you look at the mean. You look at the sample means here. So company A averages 2.026 tablespoons there. Or teaspoons, excuse me. Company B averages 2.001 teaspoons. Therefore, company A is producing more saccharin on average. Okay? But the other question is asking which company is filling its packets more consistently. Okay? So more consistently means that I need less variance. I need less spread within my data values. Well, that's what the standard deviation measures, the spread in your data values. So anytime you're dealing with the question where you're trying to figure out which data set is more consistent, you're looking for the smallest standard deviation. Okay? And in this case, if you look at it, the standard deviation for company B is smaller than the standard deviation of company A. So company B is actually producing their packets, filling their packets more consistently. Okay, so for consistency, you're looking for the smaller standard deviation. Okay. Apologize for the length of this video. All right, so the next topic, the last topic, will be the concept of z-scores. Okay, so a z-score is a measurement of how many how many standard deviations a data value is away from the mean. So the z-score tells you how many standard deviations a particular data value is away from the mean. And the way we calculate that is you take your data value, subtract away the mean, and divide it by your standard deviation. A quick note, z-scores can be negative, positive, or 0. They can be any real number. A negative z-score indicates that the value is less than the mean. You just look at the formula and tell that. A positive z-score means that your data value is to the right of the mean. And a z-score of 0 means that your data value is the exact same thing as the mean. All right, here we go. Suppose the data value has a mean of 54, standard deviation of 5. What is the z-score for a data value of 44? Okay, so the z-score formula is your data value minus the mean divided by the standard deviation. I want you guys to get used to those symbols. So our data value is 44. Subtract away the mean of 54. Divide that by our standard deviation of 5. So we have a negative 10 divided by 5, which gives us a z-score of negative 2. So the z-score is negative 2. What the heck does that mean? This means that the data value of 44 lies 2 standard deviations to the left of the mean. So the units for z-score is pretty much standard deviations. All right, that negative indicates you're to the left of the mean. Had that been a positive 2, it means we would have been to the right of the mean. All right, so what's useful about z-scores? Z-scores, what they do is they allow us to compare different data sets or different data values. Okay, so suppose a student scored an 82 on their biology test. Suppose the class average was 85 with a standard deviation of 2. Suppose the same student scored a 90 on their math exam, where that class average was a 94 with a standard deviation of 1.5. In which class did the student perform better when compared to the rest of the class? Well, you simply can't look at just their raw scores, the 82 and the 90 they scored on the respective exams. Instead, what we need to do is we need to calculate the z-score. We need to see how many standard deviations the student was in the respective classes. Okay? So here we go. Let's calculate the z-score for biology. So the z-score for biology. His data value is what he scored on the biology test, which was 82. Subtract away the mean of the biology class, which is 85. Divide that by the standard deviation of 2. So what's that? A negative 3 divided by 2, we get a negative 1.5. Okay? So his biology score was 1.5 standard deviations less than the class average. Let's figure out his z-score for his math class. His exam was, he scored a 90. Subtract away the class average of 94, divided by the class standard deviation of 1.5. Okay, this is a negative 4 divided by 1.5. And a quick little calculation here in my calculator. You get a negative 2.67 if you were to round that to 2 decimal places. Okay. So the question is, in which class did a student perform better in? Well, let's be honest. He didn't do great in any of these tests, relatively speaking, because he's below the class average. But the question is, which class did he do better in? Well, think about it. When it comes to taking exams, the higher or the more positive your score is, the better you are when it comes to taking exams. So keep in mind, these are negative numbers. It turns out that negative 1.5 is a larger number, is a more positive number, so to speak, than a negative 2.67. So that means that he did better in biology. Because that is think of a number line. To do better on an exam, you're looking at the value that lies the farthest to the right on the number line. All right. A couple more examples, y'all. Suppose the z-score for Jim's cross-country race time is a negative 0.89. Suppose the z-scores for Susan's cross-country race time is 1.5, a positive 1.5. Which racer completed the race in a faster time when compared with their respective races? Which racer had the more unusual time? Okay, y'all, if you don't learn anything else from my class, learn that context is super important. Okay? So before, we did an example where better meant a higher score. So if you're in the case where you're trying to test for better, a better exam score, you're looking for the larger z-score. Okay? But when it comes to time, when it comes to races, better when it comes to time as far as races, it's actually the opposite. Okay? In this case, the faster racer, in terms of time, will be actually the lower z-score between the two. All right, so you have to read your question carefully and understand what they mean by better or faster. But if I'm talking about a person's speed, a faster racer in terms of speed, in that case, what we're looking at is the higher z-score, because the larger your miles per hour, the faster you're going. So very important, folks. Make sure you understand what context you're working with. But for us, we are working with this context. We're dealing with time, so the z-score is related to time. So our faster racer will be the one with the lower z-score. Therefore, which z-score is lower? Jim, that has a negative 0.89, or Susan, that's a positive 1.5? That's pretty easy to see. Jim had the faster race time because his z-score is lower. Okay? All right. Do not get faster or better confused with the concept of more unusual. Okay? The concept of unusual is basically saying, okay, which z-score is the farthest away from the mean? In terms of z-scores, think of this. Think of a number line. Okay? Think of a number line. And so remember, when our z-score equals 0, that means that the data value is the same thing as the mean, right? So this is a number line of z-scores. And so let's see here. So Jim's cross-country race time was a negative 0.89. On the other hand, Susan's was a positive 1.5. So the question of unusual is to determine if the more unusual data value in terms of z-scores. Unusual means which z-score lies the farthest from 0. Okay, which z-score is just the farthest away from 0. All right. And as we look at our two z-scores here, you can clearly see that the 1.5, the positive 1.5, okay, I'm sorry, y'all, that's farthest, I'm sorry. So you can see that the 1.5 z-score is farther away from 0 than the negative 0.89. Therefore, the more unusual z-score goes with the more unusual data value, goes with Susan. So Susan had the more unusual race time. All right. So when it comes to unusual, you don't care about positive or negatives. That's why, in fact, some people say just take the absolute value and just go with the largest absolute value, but it's just a distance. Whichever distance is the farthest away from 0, that's the one that you're going to work with. Okay. All right, y'all. I promise this is the last one. All right, suppose the z-score for data value is 14. Excuse me. Suppose the z-score for the data value of 14 is a negative 2. If the standard deviation of the data set is 3, what is the mean of the data set? So to answer this question, let's remember what our formula is. Our z-score equals our data value minus the mean over the standard deviation. And then just fill in what you know and solve for the missing quantity. We know the z-score is a negative 2. We know the data value is 14. We do not know the mean, but we know that the standard deviation was 3. All right, let's solve for x bars. I'm going to multiply both sides of my equation by that denominator of 3. Okay, so 3 times negative 2 is negative 6. On your right side, you know your 3's are going to cancel. You're left with 14 minus x bar. Okay, I'm going to subtract 14 from both sides. Okay, you get minus 20. Let's pull this up. Is equal to a negative x, oh my goodness. Negative 20 is equal to a negative x bar. Let's do a different color here. We're going to divide both sides by negative 1 to get rid of the negative, and we get that 20 is equal to x bar. So the sample mean, the mean of that data set is 20. All right, y'all. I'm going to see you guys in the next video.